All right, so we're recording here on normal distributions. That's going to be the topic for the day. Last class we had a few things where we created a scatter plot and we created a dot plot and we plotted the data and we talked about the mean being the balance point. But something interesting happened is as people kept collecting more and more data, they kept seeing the same shape come up over and over again. And as they collected the data, they kept getting the same shape in many, many, many different variables. And so they named it. And it's a proper noun, and they named it the normal distribution. And the normal distribution is what we're going to be studying today. And it's not all distributions are normal. It's a specific type of distribution, and not any distributions are exactly normal. They're all approximately normal. Once again, normal is the name of the distribution. It's not an adjective. That's a proper noun. So, and here's a picture of an example of a normal distribution appearing. This is some women's college in the 70s, and they lined everybody up by their height. You know, they put the 5-foot girls over here and the 6-foot girls over here, and they had them line up like this. And what you see is, once again, that same normal distribution. And there was a mathematician, Gauss, mathematician Gauss, who actually discovered the formula for this function. And the function is given by this formula here. Don't worry, you don't have to write this down. But it was such a big deal that when they made the German Deutschmark, which is actually not currency anymore, it's been replaced by the euro, they put his picture on it, and they put the normal distribution right in the money. Now, if we look at this formula here, it's a whole big lot of mess. But some of these things we already know about. This is a constant, pi. E, we said, is a constant as well. So the only variables are this, this, and this. And the same variable appears here. And if we look, those variables are ones we studied last class. X is a data point. But mu is the mean, is the population mean, and sigma is the population standard deviation. And so what we end up with is a curve that's defined by those variables. Now, the normal distribution comes up a lot. We have, if you take babies and weigh them and did the distribution, you'll find a normal distribution. You do height, weight, ACT, SAT scores, IQ, a lot of chemical processes, number of typing errors, anything like this, you keep seeing the normal distribution over and over and over again. So what Euler found is that in a normal distribution, the tallest point here, the center, is always going to be the mean of the population. And that makes sense. If that's the average, it should be the center. And then he found it was concave down. It was kind of curving down, and then at a point it turned, and it turned to concave up. And that point comes at the standard deviation. So if this is mu minus sigma, and this is mu plus sigma. And remember, mu's are numbers. This will make more sense in a second. And this is plus 2 sigma, and this is plus 3 sigma. And what we find is that we very, very rarely get any values that are more than 3 standard deviations away from the mean. That's a very, very rare occurrence in a normal distribution. And you can change the shape of the normal curve, right? If we look at the red one here, this is a mean of 0, but the standard deviation is very small, so it makes for a narrow curve. If we look at the green one here, we see it's got the same center, but it's much flatter and much more spread out because the standard deviation is higher, even though in this case they're listing the variances, which is the standard deviation squared. if we look at the blue one, once again, same center, but with very high variance, and so that curve is very spread out. And the purple curve over here is the same shape, but has been shifted to the left because the mean is no longer 0. So the basic gist of a normal distribution is it's a symmetrical bell-shaped curve, and you'll often hear the bell curve used, and whenever you hear the word bell curve, they're really talking about a normal distribution. As the standard deviation increases, the distribution will spread out and flatten. As it decreases, as standard deviation decreases, you get the opposite effect, is that it gets tighter, it gets taller and narrower. This for us isn't that big a deal, but here is what we were alluding to right here, where we said things are very rare outside of 3 standard deviations above or below the mean. Which is that approximately 68% of all observations in a normal distribution will fall within 1 standard deviation of the mean. 95% will fall within 2 standard deviations, and 99.7% of the population will fall within 3 standard deviations of the mean. Remember we talked about last class in Z-scores and using standard deviations as a unit of measure. So, what does that mean? Well, if this is the average, then between 3 standard deviations above and below, we will get 99.7% of the population. Within 2 standard deviations, we'll get 95% of the population, and within 1 standard deviation, we still have over half the population, 68%. So this is what's known as the empirical rule, and it's sometimes referred to as the 68, 95, 99.7 rule, referring to plus or minus 1 standard deviation, plus or minus 2 standard deviations, or plus or minus 3 standard deviations. And this seems like a whole lot of gobbledygook and a whole lot of who cares. And once again, we can cut these pieces up and look at them. So if between here and here is 68, because it's symmetrical, then this part here is half of that, or 0.34. And so we can see each one of these little pieces has approximately that much of the graph in it. So, find a normal distribution that has a mean and a standard deviation of sigma. Find the probability that x will be greater than or equal to mu plus sigma. So this is mu right here. So this is mu plus sigma. So what's the question is asking is, what's the chance you'll get a number bigger than that? And knowing what we know before is this is symmetrical. So this is 0.5 because it's half the graph. Remember, the graph goes from 0 to 1. So half the graph is 0.5. Now we said from here to here was 0.68. So half of that is 0.34. So the area in red total is 0.84. Now if the area under the graph is 1, then this is going to be 1 minus 0.84, or 0.16. So this is 16% of the graph. You can never get an answer less than 0 or greater than 1. For the second one here, it says, what is the probability of being between -2 sigma and and sigma here. So we just established that this was 0.34 here. So then the question is, how much is this piece over here? Now remember, the empirical rule was 68, 95, and then 95.7. So from here to here is 95, then this is going to be half of that, which is 0.47. And so this is going to be 0.475 plus 0.34, which is going to give me, no, hold on, getting a phone call. All right, and I'm back, sorry about that. So we got 0.475 plus 0.34, and this is 0.85, or 81.5% of the graph. So let's, now I know we've reached a big time who cares moment. And so let's bring it back to some real world stuff. The time it takes your bus to get to school is approximately normally distributed with a mean of 12 and a standard deviation of 2 minutes. So how often would you get to school in less than 2 minutes? So let me just do this. And let's put some numbers to some of this stuff. So it says that we have a mean of 12 and a standard deviation of 2. So that means that this is going to be 12 minutes. The center of the distribution of the time it takes the bus to get to school is 12 minutes. Now the standard deviation is 2, so this is going to be 14 minutes. This is going to be 16 minutes, and this is going to be 18 minutes. Because we're adding a standard deviation each time. To go the other way, we take away a standard deviation. So this is going to be 10, this is going to be 8, and this is going to be 6. Remember, because this is mu minus sigma, mu minus 2 sigma, and mu minus 3 sigma. Mu plus sigma, excuse the bell, mu plus 2 sigma, and mu plus 3 sigma. So the first question was, how often do I get to school in less than 10 minutes? So that's going to be that area of the graph. Now this is 0.5, this is 0.34, because remember, half the graph is 0.5, and from here, from 10 to 14 is 0.68, so from 10 to 12 is half of that, or 0.34. So 1 minus 0.84 is 16% of the time. What percent of the time does it take between 12 and 14 minutes? So that is from here to here. Once again, from 10 to 14 is 0.68, so half of that is 0.34. So the answer to that is 34% of the time. You ride the bus 50 times, how many trips would you expect to take more than 12 minutes? Well now it's getting interesting. So, what is the probability that we will take more than 12 minutes? Well, that's this whole half of the graph, which is half of it, so that's 0.5. But it didn't ask me a percent, it asked me how many times. So I would go 50 times the probability, and I would get 25. You would expect to take the trip to take more than 12 minutes, about half the time, or 25 minutes. Or 25 bus trips, 25 trips. Now, the next thing they did was, so the standard is that they standardize it, is they created a table for all the normal distributions that had a mean of 0 and a standard deviation of 1. And we can turn any normal distributed variable into the standard normal curve by taking each data point and turning it into a z-score. And this is what I used to have to do way back in the dark ages when we wrote dinosaurs in school. Is if they asked you what was the probability and it didn't fall exactly within 1 or 2 or 3 standard deviations above or below, we'd convert it to a z-score, and then we went to this crazy table of values. And you look up the z-score and you'd calculate and you'd find the probabilities. By the way, we'll see some probabilities that we should recognize. Is if we look, hold on, a z-score of 0 is 0.5. It's because it's half the graph. And so we'll see numbers that we recognize. And so that's what we had to do, is you would take the table and you would go, okay, what is the area to the left of 1.5? And I'm just going to do this one real quick. What is to the area to the left of z negative 1.5? So then you would come to the table and you go to negative 1.50 and you'd find that answer. And this table is going to come when you take the SOL. Don't worry, you're not going to have to use it. And the answer is 0.0668. And we would do the same thing. You know, what is the area to the right of 2? And this time, though, if you look, the right of 2 is we'd go to 2 and we'd find it. But this is the area to the left of it. To find the area of it, we'd have to do 1 minus 0.9772. And that's what we used to have to do, and that's how you use the table. If you would like more experience using the table, feel free to see me after school. Instead, what we're going to do is we're going to use the calculator. And we're going to use the normal CDF. That's the one we're going to do. We may do some work with inverse norm. We'll see. But mainly we're going to use normal CDF. And so here's where it is. So if you look at your calculator, right here above vars is distribution. So I'm going to pause because if you don't already have a calculator, you should have one. So get a calculator. And we're going to use number 2, normal CDF. You would select that. And when you do, you'll see this menu. This menu has some cool stuff. It has mean and it has standard deviation. So whatever our population is, we would put that in. And then it asks us for what our lower limit and our upper limit is. The areas we're going to look behind. Remember, this is scientific notation. So the number you see there is 0.0 with 99 zeros and a 1 all the way at the end. And negative. Oh, I'm sorry, that's not correct. That number displayed there is negative 1 times 10 to the 99th. So negative 1 followed by 99 zeros. Or this is, as far as the calculator is concerned, negative infinity. If you can't type that, just type in a really large negative number, negative 9999999, hit a whole bunch of 9s, and that'll be negative infinity as far as the calculator is concerned. Same thing for positive experience. So, in the 2000, let's do a real-world example. In the 2008 Wimbledon tennis tournament, Rafael Nadal averaged 115 miles per hour on his first serves. Assume that the distribution of his first serve speed is normal, with a mean of 115 and a standard deviation of 6. So we know we have a mean of 115 and a standard deviation of 6. About what proportion of his serves do you expect to be over 120 miles an hour? So what we're going to do is we're going to go to vars in the calculator, go to normal CDF, go to distribution, go to normal CDF, and we're going to put in our limits. So our lower limit is 120, because we didn't ask if he can serve below 120 miles an hour. It was over 120 miles an hour. We didn't put an upper limit, so we're just going to type in a whole bunch of 9s to do infinity. We'll type in the mean they gave us and the standard deviation, and then you will select paste. And when you do that, you should get this answer in your calculator. And so what proportion of his serves? About 0.2023 or 20.23% of his serves will be over 120 miles an hour. And really, once we get into this, it's not real hard. You just put the lower limit, the upper limit, and the median, and the standard distribution into the calculator, and it will give you your values. So, what percentage of ASERVs would we expect to be between 100 and 110? The mean and the standard deviation haven't changed, so we just go to distribution, select normal CDF, and then the lower limit is 100 and the upper limit is 110 because we want to be between them. Mean is still the same, standard deviation is still the same. Once you get it all in, you click paste, and we get this, 0.961. So around 19.61% of the time, we're getting ASERV between 100 and 110. So, what happened? I'm missing something. So what's more likely? I don't know where. It's supposed to be something here. So what's more likely? ASERV over 120 miles an hour, or ASERV between 100 and 110? Well, it's close, but it's slightly more likely, 20% versus 19.5%, that he ASERV would be over 120, but it's going to be really, really close. Let's put it all together with one last problem here. So, data indicate that the mean length of a certain species of scarab beetle are approximately normally distributed, with a mean length, so mean of 1.25, and a standard deviation of 0.12. If you collect 500 beetles, about how many would you expect to be over 1.3 centimeters long? So my lower limit is going to be 1.37. My upper limit is infinity, because they just have to be bigger than that. That was this. There's actually two questions, so we'll answer this one first. So what we would do is we would fire up our calculator. Oh, sorry, it's going to take me a second to fire up my calculator. Well, I wanted it over here. And we put in, oops. We bring up our calculator. And our lower limit, we said, was 1.37. Sorry, I have a little trouble with the calculator. 1.37. Our upper limit, we said, was infinity. Our mean is 1.25. And our standard deviation is 0.12. So then we'd paste. So we'd hit enter, and you get the standard deviation. You would get 15.8% of the beetles that we would expect to collect would be over 1.375 centimeters. But it didn't ask us what percent. It didn't ask us what percent. It asked us how many of 500. So what we would do is we would just take the population, 500, and we're going to multiply it by the probability that we would and we can once again go back to our calculator. And we can just multiply that number by a little bit more space, 500. And so we would expect, approximately 79 beetles. And we could do the same thing with the second one. It's just that for this green one, we would have a lower limit of 1.2 and an upper limit of 1.3. And once we got the probability, we'd multiply it by 500. So that is the lesson on normal distributions. You have the worksheet in front of you. You may work in small groups. Use the calculator. Get comfortable using doing the normal distribution calculations on your calculator.